Welcome DKP Sogong aboard. Your learning journey starts now. Ever heard of a math problem that's been kicking around for 50 years, yet still no one's cracked it? That's Frankl's union closed sets conjecture. The gist? In any family of sets where taking unions keeps you inside the family, some element must be super popular, appearing in at least half the sets. Sounds simple, right? Well, buckle up. So how do we even start tackling this beast? Instead of chasing the abundant element, let's flip the script. Let's look at what's missing. Define D as all the subsets not in our family F. Here's the kicker. Theorem 1 tells us Frankl's conjecture is exactly equivalent to saying there's an element I that appears in at most half of these missing sets. Why? Because in the whole universe of subsets, every element is in precisely half of them. So, if an element is less than half in the missing ones, it must be more than half in the present ones. This shift from presence to absence is crucial. It lets us analyze the blocking sources directly. Now, let's get structural. Think about why a set is missing. Theorem 2 gives us the decomposition hitting property. For any missing set X, if you try to build it by unioning two smaller sets A and B, at least one of A or B must also be missing. It's like a gatekeeper. And get this. Theorem 3 shows we can build our union closed Flanslam F by starting with all possible subsets and legally deleting the missing ones, one by one, always starting with the smallest missing sets. Each deletion keeps the union closure intact. Finally, Theorem 4 nails it down. The most basic missing things are singletons. If a set is missing, you can break it down until you hit a single element that's also missing. These are our fundamental sources of missingness. Okay, so we have these source cores kappa of x and complete missing intervals open parentheses kappa of x, x close parentheses. Within each interval, generated by a source block, S of x, Theorem 6 reveals something fascinating. Every element in S of x actually appears in more than half of the sets within that specific interval. Hold on, doesn't that mean we found our abundant element? Nope. This is where the plot thickens. It's a self-falsification result. Local richness doesn't automatically translate to global balance across all missing sets. The challenge is proving that despite these local biases, globally, some element I must have its signed surplus sigma I of F equals Q minus 2di be non-negative. This is the crux. So, where does this leave us? We've built a fantastic machine, the legal deletion chain, the source cores, the hitting property, all working perfectly. But it doesn't quite deliver the final punchline. The remaining difficulty, the entire conjecture compressed, is called U9, the signed source balance lift. Proving this requires showing that globally, across all these source intervals and their overlaps, the contributions balance out such that sigma I of F is greater than or equal to 0 for some I. This likely involves sophisticated tools like Hall-type matchings, controlling how different source structures project onto classical sets, and maybe even information theory. The journey continues.